That's important. Okay, good. Um, just not too much being on. All right. Yeah, I can go through that really quickly too. Um, so like for those with the wavelength stuff,
Mm-hmm.
that's speed of light is equal to lambda v, right? So lambda is wavelength. This is what wavelength is.
Yeah.
Oh, so yeah, this is wavelength, right? This is frequency. Okay. And if you
Yeah.
see here, right, it's like lambda v, right? So this is
Mm.
an indirect relationship. It's kind of like PV, right? PV is an indirect relationship. Lambda v is also an indirect relationship. So when lambda increases, when wavelength increases, frequency decreases.
Yeah.
Yeah. So that's all about like plugging and solving, right? So um frequency is always shown in like negatives, like s negative, like s to the -1 or hertz, right? Lambda is usually expressed with
Nanometers.
yeah, nanometers, right? And so the problem is that sometimes speed of light is expressed in meters per second. And so I think a big problem with this, or a lot of trying, a lot of people struggle with like converting meters to nanometers, right? Um, so I kind of just memorize like by like repeatedly like trying to make like some sort of rhyme, but it never rhymes. It's like milli, micro, nano, pico, right? So milli is -3, right?
Hmm.
Micro is -6, and this is all like relative to meter, right? Milli is -3, micro is -6, nano is -9, right? So for every 1 meter, there is 10 to the 9 nanometers.
Yeah.
So like those, if you know that conversion, then the steps to this problem shouldn't be super bad. Um, is there anything specific about the problems that you get like confused with?
Okay, there's one on the first exam. I don't even know. I can't even realize what my thought process was. Wait, so V is frequency. Okay, yeah. So, the question was, numbers. It was like which of the following correctly ranks the photons in order of decreasing energy, and then
Mm.
photon number one had green light, and
Oh, so that's not really a question that's about the electromagnetic spectrum. So
yeah,
that's not something that's on you. I honestly forgot that myself. So basically, like, what's it called? You're gonna have things that are increasing in wavelengths, right?
yeah,
Um, and like increasing in frequency this way, right? And then likewise, this is also increasing in energy. Okay, so frequency and energy are directly proportional.
and
Energy and wavelength are indirectly proportional. And
yeah,
so you gotta memorize the this is for everyone. You guys gotta like memorize the what's it called? The electromagnetic spectrum.
yeah. I
So
think
like
I'm
there'll
right.
probably be what's that?
Oh, no, never mind.
Yeah, there's gonna be some sort of question asking you there probably will be some sort of question asking you to rank these, and so it's gonna be annoying. So yeah, just make sure you look at that. Don't yeah, don't feel bad if you don't remember this. I don't even remember this stuff. I so yeah. All
Uh,
right.
Yeah.
All right. Okay, well, I will get started. Um, Hello everyone. My name is Luke. Welcome to this final SI session. It's very nice it's been such a pleasure to work with you all and like just help you guys and see you guys and grow with you guys and just be there for you guys like as a role model and whatnot. Like, and I hope to continue to do that on campus. If I hope, I mean, I hope to be your SI next semester, but we'll see what happens because yeah, we'll just see what happens. You know, nothing's ever like guaranteed, right? So, but that being said, you know, even if I'm not, you know, hit me up. I'm always here to help out with whatever. Unless I'm not, because you know, next semester is gonna be a little tough. So we'll see how we'll just see how it goes with next semester. But I hope to continue to be there for you guys and whatnot. But anyways, yeah. So this is our last session, and we're gonna go over the last three modules. And these are the more like mathematical modules that Yusuf was talking about. In module 6, we really like started talking about the basis of all these things, like going from moles to moles to molecules and just like converting units and whatnot. But this really is the bulk of what chemistry is. And a lot of these concepts will continue with Gen Chem too. So it's really important to know stoichiometry. It's really important to know how to convert units and stuff like that. So out of all the modules, I would say module 7 is probably the more important one, just in general for next semester as well. So how do we balance chemical equations, right? So this is stuff that's going to be definitely on your test, how to balance these chemical equations. Something to note is this is actually a redox reaction, right? If you look at here, right, let's try to rank these oxidation states, right? Element oxygen would be 0, hydrogen would probably be +1, and carbon would have to be -4, right? But then over here, oxygen is -2, so this has to be +4, right? And then it's +1 and 0, or not 0, -2. So as you can see here, this is a redox reaction. So anytime you see a combustion reaction, and a combustion reaction is just an organic molecule reacting with oxygen, you're gonna get a redox reaction. A redox reaction is when the change in electrons, right? So you see here how this is a 0 charge, right? And then it goes to a -2, right? So that means that it actually got reduced, gaining electrons. So reduction is always gain of electrons, and um, oxidation is always loss of electrons. You see here it goes from -4 to +4. That means that it gained 8 electrons. All right. So it's something good to know, just in general, because you can have redox reactions on a ton of things, but it's important to like be able to identify that. Um, yeah, I just know it as a fact that like combustion reactions are redox reactions. But yeah, like it's important to just be able to kind of like recognize those things. So yeah, um, does any of you guys want me to go into like balancing things in depth and whatnot? Like these like basic things.
No, I don't think so.
What was that?
I said I'm pretty good with those.
Oh, okay. Does anyone else want me to go over it or not? Okay. All right. So, yeah. So balancing these things is really important. Um, because yeah, you're gonna see this for both your gas chemistry, your gas questions. You're gonna see this later in chem, and yeah, it's just good to know that. Um, yeah. We'll just go through one problem. Let's do this one, right? Decomposition of sodium nitrate into nitrogen gas, oxygen gas, and liquid water. All right, so how would we do this? We would say this is, what's it called? What's ammonium? Ammonium is NH4 plus, nitrate is NO3 minus, so you would get NO3 like this. This is the formula, all right? Make sure you guys memorize those polyatomics. And so it decomposes to nitrogen gas, oxygen gas, and liquid water. So you're gonna have H2O. Oh yeah, remember the states of matter. That's really important. So it's solid, right? It's liquid here. Nitrogen gas is gas, and oxygen gas is gas, right? So how would we balance this? I already see that first we need at least a 2 here, because the 2 here would get this to be 2, right? And then I also see here that there is, let's see, there is 8 hydrogens. Let's try 8 hydrogens here. And there's already 6 oxygens here, so there needs to be 6 on the right side, and there's already 6 on the right side. So yeah, that's how you would do that. I guess like a good strategy is to identify like what what specific elements are needed, right? So I identified that nitrogen, there need to be 2 nitrogens here, right? I identified it that only this like water only is the only thing that has hydrogen. So I like figured out that this would be 8, right? And then from there I just checked out the leftover oxygen and realized, okay, that's how it is. So yeah. All right. So yeah, so now classifying chemical reactions. So it's important to be able to classify this. Precipitation reactions, those are generally classified using the solubility rules. And so this is where the net ionic, the ionic reactions come into play, like knowing how to go from the normal reaction to the net ionic reaction. Here are the solubility rules. I believe these are given on the test. So make sure you use this wisely, because most of these questions, right? All it takes is just you to like mess these like all of these questions take is for you to actually like look at these things and recognize the like if this is a soluble or insoluble thing, making a precipitant or not. All right, so yeah, I'm not gonna go into this and whatnot, but yeah, it's still good. So yeah, here's the ionic stuff. So yeah, let's say you have NaCl reacting with silver nitrate, right? This would form AgCl plus sodium nitrate, right? Everything's balanced, right? What's the oxidation state for what's the charge of silver? Can anyone tell me what the charge of silver is?
+1.
Yeah. So yeah, silver is an exception, right? Silver is an exception. Zinc is an exception. It's +2. Cadmium is +2. Can you guys correct me if I'm wrong? Is cadmium +2? I believe it is. If it is,
Yeah,
it
that's
is.
correct.
All right, let's go. Let's go. Okay. So yeah, so you see here, this is a like reaction, right? The complete net ionic reaction would be all the charges, right? So this would be Na plus, Cl minus, right? Plus Ag plus NO3 minus, right? Yeah, I'm sure you guys did a ton of active and it was really annoying, right? AgCl, however, is solid because of the solubility rules. If you look here, it's insoluble, except it's insoluble with silver. So it's good to know that. Also, just a FYI, your solubility rules actually tell you the charge of silver. It's plus. So that's actually an interesting thing. Okay, anyways. And then you get plus sodium nitrate, right? So like math, right? You want to cancel out like terms, and that's how you get the net ionic thing. So let's see here. You have sodium here that cancels out with here. You got nitrate here that cancels out with here. So then the spectator, whatever, the net ionic thing would be Cl minus yields AgCl. All right. And you make sure you put all the states of matter, right? Aqueous. Well, actually, you don't really need to do it. It's a multiple choice test, so you can be as messy as you want, as long as you understand what you're doing, right? So then yeah, acid base reactions. This is wait, before I go continue, does anyone have any questions about anything that I did? Okie dokie. Yeah. So basically, next is neutralization reaction. This is with an acid and a base, and generally this forms water and a salt. That's always what the reaction will be. And yeah, this is definitely going to be tested a lot next semester. You guys are gonna either love it or hate it. I hope to make you guys love it, but we'll see how it goes next semester. So yeah, it's good to know all these strong acids, right? These are the strong acids Yusuf is going to use on his tests. So it's important to know that. And then, yeah, like you don't need to know any weak acids right now. Oh yeah, these are like my slides from last year. That's why I have some notes on this. Um, anyways, so yeah, this is a redox reaction. So synthesis reactions are redox reactions. You're going from elements, right? These are 0 and 0, right? And then this is +1, -1. Decomposition reactions are also redox reactions. If you can identify what is decomposition or synthesis or whatnot. Synthesis is generally like synthesis reactions, like he didn't go over like the type of reactions there are, but like basically synthesis is like going like from elements becoming like a compound. Decomposition is a compound becoming its elements, right? So it's something I like to use to like identify whatever stuff, but he doesn't really specify the reactions and types of stuff. Okay. So yeah, the key concept is to when balancing is to make sure everything is conserved, all the atoms and whatnot are conserved and yeah. All right, so balancing redox reactions. Everyone probably is not that probably don't like doing this stuff, right? I can teach you guys how I do it. And if it doesn't work for you, it doesn't work for you, do your way, right? But I'd like to do this to like make sure I know what I'm doing, right? So the first step is to that I like to do is I like to identify what is the oxidation states, right? So hydrogen would be +1 in this case. Oxygen would be -2. This would be, what's it called? This is -6. This has to be +5. Okay. That's how, the reason why I know that is nitrate is a -1 charge. So that's how I would know that. This is +1. This is -2. This has to be +5 again. Yep. Okay. And then right here, this would be -2. So this would have to be +2. And then over here, this would be -2. This would be +1. And what's it called? Maybe 3 +1. So you can just do math if you're confused, right? So this would be -8. So you'd need a +5 to make this 0. So this would be +5, right? And here would be +1 and -2. All right. So what is being oxidized? Can anyone tell me what's being oxidized in this case? Or did I do this right? I don't think I did this right. Give me a moment. Give me 1 second. I did not do that right. Sorry. This is +3. Sorry, guys. And this would be -2. So then what's it called? +3 -2. In order to have a balanced thing, you would have, sorry, not -2, -6. You have to have a +3. So this is +3. Okay. Does everyone understand how I'm getting these oxidation numbers, oxidation states?
Yeah.
Okay. Yeah, so what's being oxidized? Can anyone tell me what's being oxidized?
The
Mm,
arsenic?
Yeah, the oxidation is happening with the arsenic, right? So this is getting oxidized, right? And then over here, this is getting reduced, right? Typically, I like to say like things that are getting reduced are becoming more negative, right? And so the n is from +5 and it's becoming n +3 or +2, sorry guys. Yeah. And then the arsenic is going from As +3 to As +5. All right, and +5 right there. All right, so that's the first step. I always like to identify what's going on and what's happening. So this is arsenic is getting oxidized, right? So it's actually losing 2 electrons. How do I know where to put whatever, right? There's a conservation of charge and mass with redox reactions. With every reaction, there is a conservation of charge and mass. So as you can see here, right, it's losing 2 electrons to become a +5, right? Think of like the negative, right? It's +5 -2. For here, it's gaining 3 electrons to become n +2, right? And so the way I like to do this is I like to just kind of make sure that all the electrons are like are equally transferred, right? So this would be 2 and this would be 3, right? How do I do that? Because in order to have an equal transfer of electrons from 3 and 2, you would have to have a common, like you have to multiply them to make sure that they're both equal to 6 electrons, because that's the equal common denominator or whatever between the two. So now, yeah, Professor Yusuf doesn't really teach you guys the half reactions right now. And I honestly think that it kind of confuses you a little bit. Does everyone understand what I just did here? With the electrons and stuff?
Can you go over that again?
Yeah, sure. So basically what I did here is I identified what is being oxidized and reduced, right? And so I wrote out the charges of here, right? So there's n +5. This is unbalanced, by the way. So that's something to know as well. It's an unbalanced equation. And so what I did first is I identified like the n +5, right? And I identified the n +2. So that means that it's getting reduced, right? So that means it's gaining electrons. So essentially, this is combining with the n +5 is combining with the 3 electrons to become n +2. All right. And the same thing goes with arsenic, except now that's losing 2 electrons. And the way to make sure you're doing this properly is to make sure the charge on both sides is equal to each other. All right. And so from there, what I like to do is I like to show like this is a gain of electrons. When something is reacting with something, they're combining to gain, right? And something when something's being when something's being released, it is on the product side, right? That's because it's being oxidized. Oxidized is a loss of your electrons, right? And so what I like to do is I always like to just multiply. In order to have a balanced charge, you will have to multiply the electrons in order to make it both the same number, right? And so for two, for the top one, for reduction, you have to multiply by 2 to make that 6 electrons. And here you have to multiply 2 to make by 3 to make it 6 electrons. And so then, right, what happens is you get n plus 5, right, plus 6 electrons yields, or sorry, plus as plus 3. If this is confusing you guys, then I will move on because yeah. But I think that if you guys actually try practicing this, all these oxidation questions wouldn't be as like overwhelming. So this would be plus 6 electrons plus 2 and plus 2. And as you can see here, right, all the charge and mass is sorry, I did not add the 3 here and the 3 here. So all the charge and mass of these things are actually preserved and the electrons cancel out, right? And so then what you can do is you can take these coefficients and put them in the front of these things and you'll see that they're all balanced. All right, so this would be 2. This would be 3. Because there's 3 arsenic in the redox reaction. Here it would be 2. And then here it would be 3. All right. If you guys are confused with this, you don't have to do it. You can just do it the way you normally do it. But just this is my rule of thumb for doing these kind of questions. But yeah, does anyone have questions with what I did here? Okay, dokie, I'll move on. So stoichiometry, this is the stuff this is the meat and bones of this topic, right? How do we take mass and use a reaction to convert, like to predict a specific product, right? And so yeah, we use the reaction ratio, right? This is really good because this is a mole ratio, right? So for every 1 mole of methane, you're reacting with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of H2O. These ratios are really important because you can use dimensional analysis to get the proper like what's it called? To get the theoretical yield of something, or it's a theoretical amount of reactant you need to react with whatever stuff you have. So does anyone want me to go through any of these examples or anything? Okay. So yeah, limiting reagents is a little bit tricky. But the important thing is that as long as you just use dimensional analysis and convert it to whatever product you have, the one that's less would be the limiting reagent. And yeah, does anyone have any questions about limiting reagents or anything about how to solve them or just any questions in general? Okie dokie. So yeah, this is an important thing. This is actual yield over theoretical yield, right? Times 100, right? So that is an important thing because they might ask you, what is the percent yield? Or they might even ask like, if the percent yield is this, what would the actual yield be? So this equation is pretty important, but remember it's part over whole, right? So the actual yield is the part, right? The whole would be the theoretical yield, right? The theoretical yield would obviously be bigger than the actual yield. So I think there's a little bit of continuity, not continuity, like intuitiveness with like these kind of formulas and stuff. So you don't need to like memorize. If you just like understand, like, yeah, it's actual over theoretical, then yeah. Yeah, does anyone want me to go over any of these questions or anything in general with stoichiometry? Okay, yeah, so this is quantitative analysis, right? This is I don't know. These are just this is an extra like section I can just add it for whatever reason. Titration is important. Titration is like there's some reactions where or some questions where acid will be titrated with a base, and that's simply just an acid-base reaction. Yeah, as you can see here, this is an acid-base reaction. Yeah, these are just like the word kind of problems with these, and it's important to just recognize what's actually happening. So in this question, right, they tell you what formic acid is, they tell you what the base is, right? And it's being what's it called? What is happening here? This the formic acid is doing dissolved into distilled water. Reach its endpoint, 37.75 milliliters of KOH is required. Yeah. Sorry, my work was really bad there, like in terms of it looking normal, but yeah, essentially it's just asking how much KOH would it be required to neutralize all of formic acid. And so it's just a simple writing out the equation like KOH, right, plus formic acid, right? Formic acid is a one is a monoprotic thing. That's important. Monoprotic is one H. I think it's diprotic, that's two H's, and triprotic is three H's. So he can ask like some sort of organic acid and say like this is a triprotic thing, right? Um how much base is needed to neutralize this whole thing, right? So it's important to recognize those things. So this is a monoprotic thing, so it's CH2OH, right? Or sorry, it's CHO2H, right? So yeah, this is so it's important to be able to recognize and write out these reactions. So the reaction would be something like this with CH2O or CHO2 minus, or no, not minus. So like this H would come off, right? And making this a minus charge, right? So that would be the thing, and then you have H2O, right? So it's again acid base, or sorry, this is a base, and this is acid, and you're forming a salt and water. Okay, all right. And then yeah, you just use this reaction ratio to figure out what's going on. Yeah. And then there's gravitational analysis. This is just separation, whatever. Yeah. Does anyone want me to go through any problems, any practice problems, anything of that nature? Okay. Okay, any questions about module 7 entirely or anything like that? Okay. Now you guys are chilling. Sounds good. Yeah, so thermochemistry is important. As you saw from the last test, I'm sure a lot of people had that one question about Snickers, and I'm frankly also a little bit annoyed because I also what's it called? I also fully believed he would make Q bomb or the energy absorbed by the Snickers question, like the energy released by the Snickers would equal Q bomb plus Q water. I think the problem with that question is he didn't specify the heat capacity. He didn't say the bomb heat capacity is whatever. He said the bomb calorimeter heat capacity is whatever. So it's a really annoying, like minute detail. So I don't know. That just annoys me. But we'll see how the test goes. I'm pretty sure it won't be like that. It probably will be something like what you guys had on the modules. Because yeah, I kind of think that was a little tricky there.
Is it
Um,
possible to go over that question?
yeah, we can go over that question. Yeah, I don't have your test, but if you can show me the question or email it to me right now, I could go over it.
Sure.
But yeah, what's it called? This is thermochemistry. It's about just energy. You don't really need to know potential or kinetic energy yet. You'll need to know it for physics. But now it's like whatever, right? Temperature is a quantity that measures the express like a hotness. I don't really like this definition because in high school I learned that temperature is the average kinetic energy of a substance. Obviously, you can know that now because we did the gas laws, right? That's like we'll go over that in a bit, but yeah. Yeah, and then thermodynamics, just endo and exothermic, right? Exothermic's releasing energy, endothermic's gaining or absorbing energy, right? And then yeah, just knowing the joules and calories, right? These conversions, I'm sure everyone is now familiar with these conversions. One big calorie is equal to 1,000 calories, right? This is I don't know why it's like this, but yeah, so it's important to know these conversions. And then yeah, heat capacity. This is the amount of heat needed to raise well, amount of energy needed to raise the temperature of a substance 1 degree Celsius, right? Yeah. no one really likes using this thing because different things. Oh, if it's not as like, for example, this pan, right? It might be made of different molecules, not just like iron or steel, or like it can be made of like some plastics too, right? And so because of that, you can't really find the specific heat of that, and so you have the heat capacity of it, which is a little bit different. The specific heat capacity is about 1 gram of a substance up 1 degree Celsius. So this is Q equals MC delta T, or Q equals MCAT. And yes, C equals is the amount of energy required to raise the temperature of a substance 1 degree. Yeah. So yeah, that's basically that. And then heat capacity is just that, except instead of grams, it's moles. So that's important to know as well. Yeah. So does anyone want to go over this question? This is a question about heat absorption and heat release. Or no, not even what's that?
Can you just go over it just to refresh memory?
Yeah, sure. So what's it called? This is so now we have to, this is not yeah, this is for, as you can see in this, sorry. Okay. So you have a metal, right? And it's 52.7 grams, right? 52.7 grams, and it absorbs 362 joules of heat. And what this does is it increases its temperature from 22.5 to 37.8. And so just thinking about it like intuitively, right? This temperature is increasing, meaning that the energy is being absorbed, right? And so yeah, it says it right here. It's being absorbed, right? So now it's asking to identify the specific heat of this metal. I believe this was like a question kind of on your test. And so yeah, so the first thing you want to do is you want to put the equation. All right, and so yeah, what do we have? We have mass, right? This is a mass. We don't have specific heat. We have delta T because that's 37.8 degrees Celsius minus 22.5 degrees Celsius. And we have Q. Q is 362 joules. Okay. And so in order to find C, you just kind of isolate it. So it would be 362 joules divided by 52.7 grams times this value. So it would be 37.8 degrees Celsius minus 22.5 degrees Celsius, right? All I'm doing is just rearranging the equation so I can get C, all right? And let's see if I have my calculator on me. Yeah, I do. I do have my calculator. So what's it called? This is 362 divided by 52.7 times 37.8 minus 22.5. All right, and I got a value of 0.449. And so now what you want to do is you want to look at the table and see which metal follows that. And as you can see here, it's iron. So the identity of this metal is iron, or iron, right? All right, sounds good. Okay, any questions of how I did this? All right. So yeah, now calorimetry is a little bit different than what we just did. Calorimetry is measuring heat and specifically like heat transfer, right? So as you can see here, right, what happens is, let's say there's some sort of reaction occurring in this water, right? This reaction, if it's releasing heat, the water would be absorbing that heat, right? And likewise, if the energy is absorbing heat, the water would be like releasing that heat to the reaction, right? And so that's something to kind of understand and know. But yeah, would anyone like to go over this question?
Yes.
Okay. So with this question, it's asking, right? So we have a copper coil, right, with this amount of mass, and there's 575 milliliters of water, initially at 21.5 degrees Celsius. The final temperature of the water is measured to be 42.7 degrees Celsius. Calculate the initial temperature of the piece of copper. Assume that all heat transfer occurs between the copper and the water. So I think someone just farted in the consultant hall. Okay. Anyways, okay. That was weird. Okay. So the first thing you need to do is, right, we don't have any, so let's identify what we have. We know it's copper, right? So the specific heat of copper will be something like 0.385 joules over grams degrees Celsius. That's right here, right? That's C of copper. Then we got what's it called? The mass of copper is 324 grams. And we know the initial temperature, we know the initial temperature of this. So this would be 21.5 degrees Celsius. And we also know the final temperature. The final temperature would be 42.7 degrees Celsius. Or sorry, what's it called? Sorry, we don't know the initial temperature of the piece of copper. We know the initial temperature of the water. So we need to figure out TF, but we have TI. Sorry, we need to figure out TI, but we have TF. TF is 42.7 degrees Celsius. Okay, all I'm doing is just listing out what we have, right? The specific heat of water would be 4.184 joules over grams degrees Celsius. And then the mass of the water, if we use density would be 575 grams of water, right? And we know the what's it called? We know the delta F T, right? We have temperature final minus initial. Final would be 42.7 degrees Celsius, right? Minus initial, which is 21.5 degrees Celsius. All right. So if you see here, the one variable we have to figure out is TI. And so there's a couple ways we could go about this. For one, we could calculate joules, right, from here. And then we can use Q equals M, like we can, what's it called? Use Q equals MC delta T and calculate the amount of joules, okay. We can calculate the, sorry guys. We can calculate the, what's that? The joules of, sorry, my mind is getting a little bit, okay. Sorry, we can calculate the joules that are absorbed by the water, right? So in this case, if we do that, that would be 4.184, right? Times 575 times 42.7 minus 21.3. That's what I said there, or 21.5, I'm sorry. That's why it's important to have good handwriting, because then you'll make mistakes. So here I got 51,002 joules. All right. Is everyone following with me with the steps and whatnot? Right. So I found the amount of energy absorbed by the water. So now what you want to do is you want to plug that back in to Q equals MC delta T and figure out the initial temperature. What's it called? There's a couple of ways you could go about this. If you're doing TF minus TI, right? This Q has to be negative. And the reason why is because the copper is actually releasing energy. So the sign to show that it's releasing energy would be negative. So it would be 51,002 equals what's it called? 324 grams, right? Times the specific heat of copper, which is right here, 0.385 joules over grams times Celsius. And then you do delta, you plug in the values. So we know TF is 42.7, right? And then we have to solve for TI, okay? And so when we do this, let's do this. So it'd be a lot of math. Negative 51,002 divided by 324 times 0.385. So you have to first isolate this, and then you have to, what's it called? Add this to 42, or 0.7. Wait, give me a second. You have to minus 6 to 42.7. Okay, sorry. Negative 51,002, right? Divided by 324, right? Times 0.385, right? I'm not showing the units, but you guys can know the units, right? Equals TF minus TI, right? And we know TF is 42.7. So in order to get this, you have to, what's it called? You have to add, whatever, and the final answer would be TI. See, does this make sense? TI equals was the answer 451 degrees? I'm not sure if that makes sense. Did you guys get that for the answer?
Yeah.
Oh yeah, okay, I'm doing this right. Okay, so 451 degrees. All right. Yeah. So yeah, hopefully you guys can understand that. I know I went through that little sloppily because I was a little distracted by the random noise that's insulting. This is crazy. We need a real library, guys. Okay. Anyways, yeah. Now, yeah. So it's important to be able to recognize this and all the stuff with this, right? And this sort of thing, the HCl reacting with this, and the final temperature is this. So the what's it called? I need to solve this one. What's it called? You have to. Oh, you have the initial temperatures, right? You just have to figure out Q equals MC delta T. And the thing is you have to use what's it called? Water, because water is the biggest thing in the solution, right? And so water, like any amount of HCl would make the change in specific heat actually negligible. So it's important to recognize like what's going on with the different kinds of things. Would anyone like me to go over this question or?
Yeah.
All right, I'll do it. All right, let's lock in. All right, so we have 50 milliliters of 1 molar of this, right? And we have 50 milliliters of 1 molar of this, right? So the first thing ever is to write the reaction. So it'd be HCl plus NaOH, right? And it yields H2O, yeah, plus NaCl. Okay, so salt to water, right? It's acid base reaction. So it's reacting in a 1-to-1 mole ratio. And so the first thing actually is to figure out how many things is being reacted. And as you can see here, it's actually a 1-to-1 ratio. So I already know that both things, right? It's 50 milliliters of 1 molar of this, 50 milliliters of 1 mole of this. You don't need to do a limiting reagent because you already know that they're both reacting in the same amount. So what you want to do is you want to, what's it called? Add these amounts together. So it'll be, and add the, to figure out this amount, the total heat released, right? You want to add these amounts. So it's 100 ml, right? Or 100 grams of water, right? Times that by the specific heat of water, 4.184 joules over grams degrees Celsius, times now 31.9 degrees Celsius minus 25.0 degrees Celsius. All right. And this would equal Q. And so if we were to do that, we do 100 times 4.184 times 31.9 minus 21. Sorry, 25. And I got a Q of 28.87. Is that what you guys got?
Yeah.
Okay, sounds good. And so now that question's asking how much heat is released per mole. So you want to take this value, this is joules, take this value, and you want to figure out the number of moles in this reaction or the mole per reaction. So everything in this thing is equal to 1 mole of reaction. So for every 1 mole of HCl, that's 1 mole of reaction. For every 1 mole of NaOH, there's 1 mole of reaction. So first things to do is let's calculate the number of moles of HCl. So it would be 0.50, sorry, 0.050 liters, right, times 1.00 mole over liter of HCl, right? And that makes, the reason why I did convert this is because it's milliliters into liters and then molarity, you multiply them together and you get 0.050 mole. Okay. And so for every 1 mole of this, there's 1 mole of reaction. And so this is the mole of reaction that we actually have. So what you can do is you can take this Q and divide it by 0.050 mole of reaction to get the thing. So it'd be 287 divided by 0.050. And I got 57,740 joule per mole reaction. All right. And usually this value is expressed in kilojoules per mole. So it's important to make sure you recognize the units and stuff like that. All right. Anything else going? Any other questions? Any questions about what I just said? Okay. All right. So yeah, here's another reaction where you are basically you have to add this amount to the amount of water you have. And that's because, right, mass is always conserved in everything you do, right? If you add 2 grams of salt into salt water, that cup is going to have 2 more extra grams of mass, right? And so it's important to recognize that. Would anyone like me to do this question or not? Becky? Oh, okay. So yeah, bomb calorimeters. Everyone's probably annoyed about this. But yeah. The bomb. Okay. So like as a whole, this whole thing is the bomb calorimeter, right? And so that's why the heat capacity of this was like accurate for both the water and the bomb. And that's why you couldn't do bomb, or you could do it, but that wasn't the correct heat capacity because the bomb itself is here, right? The bomb calorimeter is this whole thing. And that's why that question was wrong. So in this question, instead of what we have in the test, instead it's told the bomb itself had a heat capacity of this. What the heck happened to my, what? Hello? Oh, okay. Yeah, so the bomb itself had a heat capacity of this. So instead of what we did on the test where we did the calorimeter, the Q of calorimeter equals Q of Snickers bar. This question does Q of bomb plus Q of water equals Q of, in this case, sucrose. All right. Does everyone understand why that question was the way it was, as annoying as it may be? That was the question. And so yeah, what it's important to know is what the heat capacity thing. Heat capacity is equal to joules over delta C, right? And yeah, we have to do the Q of water plus the Q bomb to figure out the amount of energy released by sucrose. So yeah. Would anyone like me to go through this process?
Yeah, please.
All right, sounds good. So first thing is use Qmat MC delta T for to figure out the water. And for this one, you have to do what's it called? You have to use the heat capacity. You have to use the heat capacity, right? So a this is the heat capacity, right? It's joules per degree Celsius, and you have to multiply that by the delta T because what's it called? Yeah, heat capacity is joules over delta T, right? This is delta T or change in temperature, right? Then multiplying it by delta T would give you joules. So for this one, instead, what you have to do is you have to do joules over delta T times delta T. All right, so let's plug it in. Let's plug in all the values, right? So the first one is, yeah, we have 893 joules over degrees Celsius, right? And the delta T, right, would be temperature final minus temperature initial, which would be 42.3 or 42.7, sorry. 7 degrees Celsius minus 23.8 degrees Celsius, right? Plus, this one now is the water, right? So, sorry, we don't do Q equals MC delta T, we do MC delta T, right? That would equal the amount of whatever, the joules, right? So now for this one, we would do 755 grams of water, right? Plus 4.184 joules over grams times Celsius, right? Plus, or sorry, not plus, times the delta T, which is 42.7 degrees Celsius minus 23.8 degrees Celsius. Okay. And then as you can see here, this is Q water. This is the amount of water the energy absorbs, and this is the amount the bomb absorbs. All right. And so in this question, right, if we plug in all these values into the calculator, you can separate these as well and add them up as well. If what I'm doing is a little confusing. Either way works as long as you get the answer. For here, I got 16 point, sorry, 16,877, like about that, maybe 678. I'm not gonna round six until the end, so 7.7. And then this one I got 7. Oh, a little tricky. I put 7. That's a little, sorry, I messed. 777 or 775. Yeah, what am I saying? I'm sorry, guys. I'm post genetics exam. You guys will if you guys contact me, I can bless you guys up with stuff about genetics and stuff. But yeah, anyways, so this one would be 61,285, right? And then you want to add these up. So the values here will be around 78,162. I'm just gonna leave it at 3. 3 joules. And this is the amount of energy that's released by sucrose, by 5 grams of sucrose. All right. And to convert this to kilojoules, you would divide this by 1,000 to get 78 kilojoules. Is that the answer? Did I do it well?
Yeah.
All right, sounds good. You guys have any questions about what I did here?
Do we need it in kilojoules or can we just leave it in joules?
For this question, you would leave it at however you want. It didn't specify what units. Usually it would specify the units. All right. So like if it just says the amount of heat, then you can do whatever you want. However, it is a multiple choice test, so like you can see the answer choices, and if they're on kilojoules, you're most likely to convert it to kilojoules, right? So yeah, just something to keep in mind when you do these tests. All right, so now we're going into enthalpy. So I heard a lot of people had a lot of trouble with the Hess's law question and also maybe with the bond energy stuff. And don't worry, we'll get through all those. So here's delta H, right? This is for if we have this is in general with any sort of thing. If you have like this reaction coordinate graph which shows reactants and products, right? Delta H would be products minus reactants. So in this case, delta H is negative, right? This shows a exothermic reaction. In this case, delta H is positive because it's products minus reactants, right? This is a positive value while this is going down. This is going up, right? And so that's generally how it is. And yeah, as we go through this, we'll continue to do that. Yeah, this is stuff that we kind of did earlier with the acid-base question, so I'm not going to go into that. But yeah, this is the more important thing, heat of formation of stuff, right? So delta H can also equal delta H formation of products, right? Minus delta H formation of reactants. So it's essentially products minus reactants. Okay. So does anyone want to go through any of these questions? How to do the standard heat enthalpy? This stuff is pretty self-explanatory because what's it called? Yeah, this is just showing how like this is the reactions and whatnot, right? Yeah, this is the equation I just showed. It looked confusing with these summation stuff, right? But don't worry, it's just products minus reactants. Products of heat of formation of products minus heat of formation of reactants. Okay. And so this is Hess's law, and I'm sure everyone got really confused and scared maybe by the question on the test. That one involved fractions, right? So here's my like tips and tricks for Hess's law. My tips and tricks would be to see which what's it called? Like obviously this one's probably really simple, but basically to like isolate what you need and what you need to do to get a certain thing. I know that sounds very ambiguous, but essentially like you want to identify what reactions will get you the product that you need and specifically whatever products, right? If there's like I don't know if there's a good example for this. I mean, if you guys can send me, if you guys email me right now your like question from your test, I can go over that. If you guys want me to, that is. You guys need help with that as well? I'm kind of assuming here, but are you guys chilling with it or
No, can you go over it?
okay? Can you guys send me? Do you guys send me anything on Outlook or anything? No. Yeah. Can you guys send me like the question? Because I know this question's probably a lot easier. Because all you have to do is just flip one of this reaction to get whatever. But with the other questions, it's a little more challenging because you have to use fractions and stuff. I mean, this question's kind of challenging, I guess. We can try to do this one. So let's do it. Okay. All right. So when I look at this, right, I see we need this. So I look over here and it's a little confusing, right? We got 1/2 here, we got three halves here, we got twos, right? You can get really confused by looking at these numbers. However, let's like try to look at this and try to identify what we need and what we don't, right? So I obviously see that we need a fluorine in the reactant side, and the only reaction that has a fluorine is this one, and it's a 2, right? So automatically I can see to myself, okay, I have to flip this and I have to half it. And the reason why is because fluorine is specific to having 1 mole in this, right? So in order to do this, I would have to negative 1/2 this. All right. So that's already the first thing. Next thing I look for is I look for this one. Let's look for this one, right? There is only one mole, reactant in this, and that's this, right? And so in order to do this, we have to half this. Okay. And then yeah, the reason why I negative this is because this would reverse this reaction, right? In this case, this would half this reaction. And then finally, for this one, you would have to just flip this because you have 1 mole of this in here, right? So you just flip it. And I wouldn't really need like if you want to check it, you can, but technically it's all I mean, I'm gonna check it for you guys, but when you guys do this and make sure you get this reaction, what's going to happen is all these like different variables will cancel out. And I'll show you guys as I do it, but you can have confidence with just isolating the reactants and products um and yeah, just kind of like making sure you have the right ratios for the final reaction. So let me write all of this stuff out. So for the top reaction, you have F2, right? Plus 1/2 O2 yields OF2. Okay. For the bottom one, you have CLF plus O2, sorry, plus 1/2 2 yields 1/2 CL2 O plus 1/2 OF2. Right? You see how this is getting really confusing in and of itself, right? Because it's just like there's so many different things that are happening. How am I gonna know what's going on, right? So I would just reckon like if you just identify what you need and what you don't need, it's really a lot like you don't need to write out all this stuff because you already have the reaction that you need. But that my like intuition comes with like a lot of practice and stuff. And then so this here, right, would be negative 1/2 Cl2O, or sorry, not one negative, it'd just be Cl2O. Plus 3/2 OF2, right? So yields O2 plus ClF3, right? This looks pretty complicated, but it actually all cancels out, right? We have one O here. Let me use a different color. A different one, red. Okay, this cancels out with this, right? Sorry, I shouldn't do that. There is 1 mole of O on this side, is 1 mole on that side, so it cancels out. There is, what's it called? This cancels out with this. Okay. And this cancels out with this, and you get your final reaction, right? F2 plus, why is my thing not writing? Plus ClF yields ClF3. So you see how all you have to really do is just identify these like reactants that you need, figure out what you need to do to manipulate the equation to get whatever. And then you don't even need to do this stuff. This is just for you, right? You can just use these values now and automatically go and convert the delta H's, right? So like I'm just a little shortcut in case anyone's like up for time or like a little confused with this question, because there's definitely going to be some Hess's law question on here. But yeah, does everyone understand the thought process? Does anyone want me to calculate delta H? Okay, all right. So
So,
hopefully I help. Yeah.
so like for this, I think in the exam it was just kind of confusing because I was taking into account all the other variables, so you don't really need to check for everything else. Like for example, for the first one, you just
Mhm.
like for the Roman numeral one, right? You would just into like looking at the reaction on top that you would have to flip it and then just divide it by half. You don't have to look at anything else to be like, oh, like
Yeah.
does the O2 cancel out or does the 2OF? Like you
Yeah.
don't
Yeah.
really
Yeah.
have to look at that.
Yeah. So that's like the whole idea, right? The
Okay.
approach to the problem is like really important with Hess's law because if you don't know yeah, it can be really overwhelming to like look at all these O's and be like, what the hell? How am I gonna cancel all these out, right? But it's important to just like that's the little trick with like Hess's law. Like it's important to just focus on what you need, right? So that you can get the problem. And it's actually when you do that, it actually becomes a lot faster and it actually becomes an easier kind of fun problem to do because it's like kind of like a puzzle. Because
Yeah.
yeah, so like yeah, that's the exactly the approach that I'm trying to like tell you guys. Like so if yeah, so the first thing is to like isolate what you need. And if you can't do that, then you have to isolate something that you want to cancel out maybe. I believe on your test there was something that basically you had to flip something to cancel out something. It was weird, but the first rule of thumb is to always just like look for your final look for look at your final reaction and like try to see what you need to get rid of whatever. Okay. Yeah. So hopefully that helps out with some people. But yeah. How many people are in here? Yeah, is there anyone in here? Oh, there's 8 people. Wow, I have so many people watching me. Okay. All right. Okay, anyways. Bond strength. So this is now a little bit different. This is bonds broken minus bonds formed. Um, yeah, it's really just plugging in the equation and making sure you have all the right numbers. A lot of people sometimes use reactants minus products. I don't really personally use that because I feel like it can confuse you with the other um the delta H reaction, right? So yeah, I would just say to be mindful of what you use to remember this reaction. So like there's probably going to be some sort of question where you're going to have to they're going to give you the bonds and you're going to have to figure it out, right? Um, would anyone like me to go through this problem to show you the thought process and whatnot? Yeah, I mean it's pretty like I would say self-explanatory. All you have to the hardest thing is to figure out which ones you're using, right? Obviously these get a little confusing because they're like, what should I use, right? So it's important to literally just like if you need to circle what you need instead of like eyeballing it, because maybe like I can tell you there have been a lot of times where I made a mistake where I looked at CH bond, but I might have looked at the CC bond instead and then put the wrong number, right? So it's important to really like just make sure you're getting the right number and putting into the equation. Um, sorry, this is what it's called, my secret Santa thing. I was trying to figure out who has what because I knew people. Okay. Anyways, module 8 or any practice problems. You guys want me to go through this Hess's or is there a Hessel law? Do you guys want me to go through this Hessel law question as well to show you thought process and stuff?
Yeah, please.
All right, so let's see this, right? We got hydro blah blah blah, right? Peroxide, blah blah blah, and blah blah blah. So there's already, yeah, I can see how confusing this could get, right? You see here, this is C6H4, this is C6H4O2. So that can confuse a lot of people. But let's look at this, right? So, all right, so we see here that this is already good. So we can keep this reaction the way it is, okay? For this one, you have to flip this one. So let's flip it. So let's get, this would be a negative, right? And then for this one, you would have to so we have a liquid one, so we have to flip it and times it by 2. So it would be -2, right? And what's it called? Is there anything else we need to do? I believe we have done it, right? Um, okay, let's just write it out so I can make sure I did this properly. So -2 this. Oh, we have to times this by 2. That's why it was. Okay, so I'll explain why. So if you, yeah, once you make sure you have all the right things, now let's try to see if we can balance it out. Okay, so let's do this. So we have C6. Sorry. Yeah, so in the first reaction, it's gonna be H2O2, right? Yields H2 plus O2. Okay. Second one, it's gonna be sorry, it's gonna be two H2O, right? Yields this gas yields H2H2 liquid. All right. And then here it's gonna be C6H4 OH2, right? Is gonna yield D6H4O, right? Plus H2. And then here it's gonna be H2 plus 1/2 O2 yields H2O gas. All right. And so the reason why I just realized whatever is because, yeah, after you isolate whatever and you make sure you have the right things, now you have to make sure, can I cancel everything out? And so that's where I was like, oh, because you can't cancel everything out. And so as you can see here, what you need to just do here is you need to multiply this by 2. And when you multiply this by 2, right, that cancels out the, if you see here, you want to cancel out this thing, right? And if you multiply by 2, you would have to multiply this by 2 as well. And so that's why I was saying first isolate whatever you need. And if there's something you need to cancel out, figure out how to cancel it out. And so one of the things is to multiply this by 2, right? And so a common thing that people might do that's not the best is to focus on like the O2 and the H, and like it might get confusing. I would say focus on the thing that is like the most obvious thing you can cancel out. You know, in that case, it would be the H2O gas, right? So in this case now, instead of it being this, it would be 2, and then this would be that, and that would be that. All right, does everyone understand where I'm going with this, right? And so now, what's it called? You would cancel out, right? The H's. Yeah, the H's cancel out, right? Because there's 2 H's in here. There's 2 H's here, right? There's an O here, there's an O here, and now there's a 2 gas here, there's a 2 thing here. So then now everything will balance itself out and you'll get the final reaction, which is C6, H4, OH2, right? Yields C6, H4, O2 plus 2H2O, right? So you don't really need to do this stuff. It is helpful though, because in some ways, like I probably, if you just did what I told you earlier, right, you may have not been able to recognize that. However, like if you have a lot of practice and whatnot, you can recognize that and you don't need to do that. But you know, whatever works for you. If writing it out is helpful, make sure you write it out fast, and yeah, make sure you just recognize what you need to cancel out, because then yeah, these problems become from a 5-minute question to like more of like a 1-minute thing. Okay, does everyone understand where I went with this? Okay, sounds good. All right, anyone want to go through any of these practice problems? Okay, sounds good, guys. Okay, now we're on to gases. We got 25 minutes, so we're gonna make this count. So gases, I mean, I think a lot of this stuff is just plug and chug, right? With the equation PV equals nRT. Yeah, if you guys have any trouble with that, let me know. But yeah, so we'll just talk about that, right? All this stuff is pretty like I'm not really gonna be tested, right? It's just kind of common knowledge. So yeah, pressure is something that a gas is exerting on a container. That's important. So general volume is the size of the container, temperature is the speed, right? Average kinetic energy, right? It's a speed, right? And then moles is whatever, right? And then, yeah, STP is really important. STP tells you a lot of information. It tells you that temperature is at that, atmosphere is at that, and there's actually a relationship at STP. It's 22 liters per mole, right? So that's really mole of gas. So like these are really important to, I did not spell gas, right? Sorry guys. So that's really important, right? So here's all these things. They might ask, they probably not gonna ask you who made what law, but it's important to just know, right? And yeah, then you can just make the combined gas law, which is PV equals nRT. Okay. And so, yeah, the manipulation of this formula is the basis for most gas law math problems. And so, yeah, so this is the equation. And yeah, a lot of this stuff is just using this equation to figure out what's going on and stuff. So would anyone like me to go over any of these math problems? Okay,
Can we go over
Yeah.
like one?
yeah, sure. So I'll go over this one. Yeah, this one's pretty long, so I'll go over this one. So what's it called? What am I doing here? Okay. This is all the stuff I wrote last year, so let's make a big eraser. Oh, that was so satisfying. Okay. So it's important to first figure out what's going on. So you got this amount of ammonia mixed with this amount of oxygen to produce H2O and N2. So that means that the reaction's occurring. So and it's asked to figure out the volume of nitrogen and when it's collected at this pressure, temperature and pressure, right? So the first thing to do is to write the reaction. Reaction is NH3 plus O2, right? Yields H2O plus N2. Okay, so let's balance this out because it's not balanced. So you see here, there's need to be 2 here, right? And because there's 2 there, there needs to be 6 hydrogens, and because there's 6 hydrogens, right? That means there's 3 oxygens, so there needs to be a 3/2 here, right? And so because there's a 3/2, we want to multiply this by 2. So now it'd be 4 NH3 plus 3O2 yields 6 H2O plus 2 N2. All right, does everyone understand what I did here? This is all the stuff with balancing. So now what we want to do is we want to calculate the number of moles, right? We're going from this stuff, right? To figure out, it's like basically all this stuff all this information that's being given, right? Is essentially like a really big limiting reagent question, because what's happening is, if we're examining what's happening, right? This ammonia gas is reacting with this amount of oxygen gas to produce some amount of H2O and N2. We don't know what is actually limiting or what's actually in excess. So that's why this problem is a little bit tricky, because yeah, like it can be overwhelming with all the numbers, right? So it's important to recognize what we have. So this is all the stuff for ammonia, right? And this is all the stuff for oxygen. So this is the stuff for oxygen. So let's list it out, because I believe that's what he did in class as a steps. So also another important thing is all the temperatures you convert to Kelvin. So 35 plus 273 is something. It is 308, right? 308.15 Kelvin. All right. I just did 25 plus 273 plus 10, right? And then we got, that's the temperature, temp, T, V, and P. P would be 1.75 atmospheres. Looks like 2, sorry. And this is all for ammonia, right? I'm just showing all this like steps because in case you guys completely like forgot whatever, but on the test, I would just normally go straight to the question, like the mathematical problem. So now we go to O2, right? O2 is the volume is 9.97 liters, right? It is a lot more than 65.0, what's it called? 30. It is 338.15 Kelvin, right? This is T. Pressure is 2.34 ATM. So yeah, so this is PV equals nRT, right? So we have to figure out moles, right? Because we're trying to figure out the limiting reagent, right? And so we gotta do PV equals nRT, or manipulate it to be PV over RT equal that, right? Same thing with here, PV over RT equals N. All right, so let's do that. So we gotta put 1.75 times 4.75, right? Divided by 0.08206 times 308.15. And I got an answer of 0.32 8. I'm going to keep this as an exact number. So like I'm going to use the number I use in the I got in the calculator to get the final answer. All right. For the other one, it's going to be 2.34 times 9.97 divided by 338.15 times 0.08206. You guys don't know what 0.08206 is? That's a gas constant. So here, the number of moles, this is moles of NH3, this is the moles, it's 840 dot 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 point 0.0, sorry, 0.840 moles of O2. And then now you have to use the mole ratios, right? So for every, what's it called? 4 moles of ammonia, we're getting how much, yeah, for every 4 moles of ammonia, you get 2 moles of N2. 2 moles of N2. And yeah, and then for here, for every 3 moles of O2, you got 2 moles of N2. Okay. Okay, so now when you put these numbers in, right, you get the thingy-majiggy, the number. So 1/2. So here I got 0.164 moles of N2, and then here I got what's it called? What did I get? I got 0.560, right? Moles of N2, right? And also I'm just saying here, I'm using exact numbers. So this is the limiting reagent because this is the less amount of products. So this is excess. And so now what we do is we use this value to go to pressure, right? So now that we have moles, we also know the pressure and we know the temperature. We don't know the volume. So we have to solve for that. So we have P equals nRT. We use this moles and we solve for V. So it'd be nRT over P equals V, right? So you take this moles, right? So 0.64 mole, right? Times pressure, which would be 2 yeah, like that. Temperature is 47 degrees Celsius, or 47 plus 273.15, that's 320.15,
Quick
right?
question.
Oh yeah, sorry, that
Why
scared
did
me.
you multiply it by pressure?
Multiply what by pressure? Oh, you're right. That's because my handwriting is terrible. Sorry. You're 100% right. It's 0.82. Sorry, that scared me. Oh my goodness. Sorry. Okay. Yeah, you're right. So it would be the mole, the R, right? And then yeah, you're right. It would be 2. Oh, okay, my heart rate just went up. Okay, 210.8 atmospheres. Okay, right. This would be volume. So if you were to calculate this, 0.164, good catch, that was good. 0.8206 times 320.15 divided by 2.10. I got a volume of 2.05 liters. All right, is that what you guys got? If you guys did it,
Yeah.
then good. All right, sounds good. So yeah, that's the whole thing with stoichiometry. I put random things there, it's whatever. So yeah, so basically that's yeah, that's how to do that stuff, right? And so yeah, it's important to just know how to use stoichiometry and go to moles because mole goes to everything in stoichiometry, right? So now we're going to Dalton's laws of positive pressure. It's essentially just adding up the pressures to get the total pressure. Yeah, so any sort of gas that may not be mixing, right? The pressures of the individual gases in that container will equal the total pressure of the total like gas. And the same thing with the mole fraction, right? The moles, each mole of gas, right, will equal a total amount of gas, right? And that will give you the total pressure, right? So the mole fraction of one of the gases times the total pressure will give you the partial pressure as well. So those little things are important. This is essentially saying like, what's it called? Like 100, like let's say the partial pressure, the total pressure is like 100. this is like multiplying it by a fraction, right? The fraction of oxygen would be like, well, let's take 1/4, right? The pressure then would be 25, right? So it's really all about like percentages and just like seeing that. Or you can just memorize it, whatever works for you. All right, so should I go spend out some time on this? We're doing some good time. Do they want me to do this question or not? Okay, I'm like the last person here. But there's so many randoms, like so many random people just like making random sounds, you know? It's kind of it is what it is. Okay. Okay. So now this is the fusion and diffusion, right? So diffusion is just going and spreading out into the thing. Like think of like you taking your cologne or perfume, right? And you just spray it, right? It'll diffuse into the atmosphere, right? Effusion is a little different. Effusion is just going through this little hole, right? And so that's what's it called? That's what we learned about earlier. I mean, this is what this whole thing is, right? This is taking its molar mass and kind of relating it to whatever. So you basically what this actually solves for is the rate in comparison to another rate of a fusion, right? So basically, you can kind of be intuitive with this, right? If you have a gas that has a molar mass that's lower than the gas you're comparing with, the rate of fusion of that gas in comparison to the heavier gas will be higher, right? Because what's happening here is that molar mass is actually indirectly proportional with speed, right? So that means that like or effusion, rate of effusion. So that means that the smaller you are, the faster you're gonna be. That's essentially what it is. The heavier you are, the slower you're gonna be. I feel like that's pretty intuitive. So like yeah, if you see hydrogen gas and oxygen gas, what's the rate of effusion? And it's like a multiple choice question and it's like faster, slower, whatever, you can just know, okay, this is H2, right? This is O2. H2 is smaller, right? So H2 will be faster. So like little tricks and shortcuts and whatnot, right? Yeah. And then this is the KMT, right? Ideal gas law, just knowing this is kinetic molecular theory. This is essentially like what the ideal gas law is, right? And this is what it's saying. It's saying that the volume of things are supposed to be zero. As we know, that's not true. Particles do not exert a force on each other. Next semester, you're going to learn intermolecular forces. They do. And that yeah, there's only collisions between the gas particles and the walls of the container. That's also kind of not true because there's collisions between the gas particles in themselves. And yeah, like all this stuff with ideal gas law, they're just like ideal, right? They're not actually necessarily real, right? And this is the average, this is what I meant with the temperature and the average kinetic energy, because the temperature is the only thing that's actually being multiplied. Rate, the R is, as we know, like a constant, right? That temperature is essentially the average kinetic energy of a substance. And so yeah, that's real gas laws are a little different. Real gas laws have to do with like how gases really act. And so a way I remember this, and this might be a little bit inappropriate, but real gas laws are like real boyfriends, right? Oh, no, let's start with ideal gases. Sorry. Ideal gas laws, ideal gases are like ideal or dreamlike dreamlike significant others. Okay, that's what I'll say, significant others. I learned this in high school, right? So you're gonna have a hot guy or a hot person, right? And you're gonna have they're not gonna be super annoying, not annoying, right? And this is supposed to correlate with temperature, right? High temperature and low pressure. You can also just memorize it. I like to look at it like this because it's kind of fun. And then real gases are the opposite, right? They're ugly, right? And they are annoying, right? So a lot of pressure, high pressure, and low temp. Okay. I hope you guys understand that. I kind of like the little way I remember it. And so yeah, this is the Van der Waals equation. This will be on your reference sheet. So I think it's pretty good. Deals with pressure, this deals with volume. And so basically that the heavier you are, the actual, if you see here, right, you got all these gases, right? Basically, the heavier you are, the more likely you're gonna like not be following the ideal gas law. So like H2 H2 is gonna be the like most ideal gas ever, right? But then N2 and all these dips show like the heavier you are, the more you're not gonna the more deviant you're gonna be towards the ideal gas law. And so yeah, that's module 9. Wow, we made it on time. That was good. And then this is your next semester. Um, but yeah, does anyone have any questions about anything? No? Well, guys, ask me anything. Ask me any questions, any exam
question.
questions. Yeah.
So for the exam, what's gonna be like the distribution of questions in terms of like modules? Like, is he gonna put a lot more emphasis on like exam 3 material than compared to like exam 1, or how is it gonna be?
Let's see. So let's look at your syllabus. I believe your syllabus is a really good way of kind of showcasing that. So if you look here, your syllabus is this. So I believe there probably is gonna be like, I feel like this is a good distribution of questions, right? So there's gonna be like a solid like amount of questions. There's gonna be one question, like basically like kind of you can probably look at this and like figure out like how many questions are gonna be like whatever. There's probably gonna be a little bit more questions of stoichiometry and stuff, right? But like all this beginning stuff, there's gonna maybe like 1 or 2 questions about it, right? 1 or 2 questions about electromagnetic radiation, like you see what I mean? Like you can just look at your syllabus and kind of see how like what's the distribution of questions. All right. Like whatever amount of class days you guys spent doing something, that's probably the amount of questions would be on the test for those. Okay.
Okay, thanks.
Yeah, no problem. Any other questions about me? Let me like if you guys have problems you want me to go over or any sort of like questions about how to do something, anything with the whole like chapters that we went over, yeah, I'm here. Yeah.
Oh, can we go through the Hess's law for the exam 3? I don't know if I did it properly. I feel like I got
Hmm. Can you guys send me it? Just send me the question.
Yeah, do you want me to put in the chat or do you want me to email it to you?
Um, yeah, you can email it to me really quickly.
Let me-
Yeah. Your exam is tomorrow is at 9:30.
8 a.m.
Oh, and then your bio exam is at 9:30, right?
Yeah.
Oh, that's tough. I mean, we had the same thing last semester, but we had the easier bio teacher. That's really tough. Good
Who's
luck,
the
guys.
easier in your opinion?
What's that?
Who do you think is the easier bio teacher? Like you had Haji?
No, so we had a different teacher entirely. We had Dr. Callow, that's what we call her. Gianni. I don't know how to say her name, but we didn't have Haji. We had Callow. And so the reason why you guys don't have her is because she's on maternity leave. And so yeah, that's why you guys have Haji.
Oh,
It's
otherwise we would have had Kaloggianis.
yeah, Kaloggianis. That's how you say it. Good job.
All right.
Um, okay, I think I got the question.
No, that was
So
the I sent before.
oh
We're
wait,
gonna
no,
go
this is
over
my
it.
oh, there's the Hess's Law question. Oh, I see. Okay, okay, let's go over this one. Okie dokie. All right, so let's do this. So let me save this. Let me yoink this. Let me get this. I'm sorry, guys. I'm like really pooped as well because what's it called? I had an exam today, and I'm like, yeah, I came straight from the exam. That's why I'm like, if I have low energy, I'm sorry, guys. Um, let's see. How do I implement this? Image, and then we import. Okay. Hello, test question. Okay, so this one's a little bit interesting. All right, so we have to get this sort of thing. And I remember this question, it was a little scary. So basically, what you want to do first is you want to see what you need and what you don't need. Okay, so obviously carbon monoxide is probably what threw everyone off because there's multiple carbon monoxide. So like that's probably not something you should focus on. Again, there's also multiple carbon dioxide. So that's also something you probably shouldn't focus on right away. So I guess the first thing you should focus on is these, the iron and the F2O3, right? And so for this one, you want to flip this and make this -2, okay? Because we know that iron has to be on the left side. And then for here, you want to divide this by 1/3. Because if you would divide this by 1/3, you're going to get the right number of moles for the thing. And so now this is where it gets a little confusing, because now you have 2/3 of Fe3O4, right? And you have to get rid of 2/3 of FO3O4. And so this is where it gets annoying, right? You actually have to flip this and multiply this by -2/3. Okay. And so like the way okay, so let's go through what I just thought about, right? I started with first like isolating the two things I could isolate, right? The iron and this thing, right? And then I isolated it. Now, instead of like focusing on carbon monoxide or whatever, I focus on the one thing I could like see, right? There's this equation, right? And it's impacting this thing, right? So we need to get rid of iron 3O4 because that's on the equation. So you have to like multiply this by -2/3. Do you see like the thought process and stuff? If you guys are there, right? So yeah, so then now let's see what happens, right? If we were to write this equation out, we would get sorry, 2Fe plus 2CO2 yields 2FeO plus 2CO, right? That's the third equation. First, this one would be 2/3 Fe3O4 plus 1/3 CO2 yields Fe2O3 plus 1/3 CO. Okay, and then here it would be what's it called? There's a lot of moving variables here. So it'd be 2/3 CO2 plus 3 times 2/3 would be 2 FeO yields 2/3 Fe3. I'm going into the delta H's 3O4 plus 2/3 of CO, right? So it's really annoying how you have to use fractions, and sometimes it can be daunting. So let me just yoink this guy. There you go. Let's move this somewhere. Let's move. Where should I move this? I don't know where to move it. Let's move this here. Let me erase this. Okay. So does everyone understand what the thought process with what I'm doing right now? So now I'm just gonna cross out everything. So let's see what I need. So we have iron, right? Iron's there. What's it called? Iron 3,4. Let me get a different color. Iron 3,4 crosses out with this, right? FeO crosses out with this. Carbon monoxide or carbon monoxide. Where's carbon? Oh, carbon monoxide we need. Okay. And so yeah, we have 3 carbon monoxides, right? This is 3 carbon monoxides. And then we also have 3 carbon dioxides, right? So basically like the part of the reason why I did this fast is because I already did this before with like in a different SI session. So that's why I can recognize whatever. I don't really remember. I didn't remember how to do it, but I do like the thought process is how I did solve it earlier. And so basically, yeah, you just have to, what I would say is, yeah, focus on what you can definitely isolate and then focus on what you definitely can cancel out. And then everything should fall in place because all these CO2s, they're going to confuse you, right? All these carbon monoxides, they're confusing, right? So yeah, if you do this, you're going to get the product, right? As I showed. And then yeah, you can do the delta H from there. All right, does everyone understand? Okay, all right. Any other questions? Any comments, concerns, any sort of last minute questions? I'm always here to answer anything, you know, so please use me, utilize me. I'm here for you guys. Okay. Well, if not, I hope you guys like have a wonderful day. Again, it's been a honest pleasure having you guys as my kind of like students and just being able to like work with you and whatnot. And then yeah, I hope you guys have a wonderful day. Take care. And yeah, good
Bye.
luck tomorrow. Good luck tomorrow. Bye bye.
Thanks, Luke. Bye.
Yeah, no problem. Have a wonderful
Thanks,
day. Goodbye. Yeah, bye bye.
You. Oh, I have a quick question.
Yeah, what's up?
Is it still recording?
Yeah, do you want me to just turn it off?
Whatever, it doesn't really matter. I have a couple questions.